Hello, and welcome to my tutorial on using machine learning to classify sea ice and leads in satellite imagery. Machine learning is a subset of AI which gives computers the ability to learn without being explicitly programmed. With large amounts of data, we can write algorithms that learn to identify patterns in order to make predictions on future unseen data. Using satellite images as the input data into our machine learning algorithms can improve our ability to observe the Earth in real time, which can enhance a wide range of sustainability efforts in order to protect our planet. Today, we are going to look at using satellite images of Arctic sea ice to classify leads, which are cracks that are forming in the ice. Accurate detection of leads is important for marine navigation and understanding the current state of the ecosystem. In this tutorial, I will be walking through two Jupyter notebooks which contain the code for this task. If you'd like to do this on your own, I've listed some steps here to help you get started. I will be running the notebooks in Google Colab, but you can run this in any environment which supports Jupyter Notebook. I'll be linking the folder which contains the data and the notebooks for you to download in the caption below. This first notebook is used to create the training and test data sets that we'll use to build our models. We'll start by installing and importing the packages that we'll need to run the code below. Next, I mount my Google Drive so that I can import data directly, and then specify my local paths where my data and outputs will be stored. Be sure if you're following along on your own to replace these paths with your own local paths. To construct our data sets, we will be using a single Sentinel-3 image of Arctic sea ice, overlaid with a map that I generated using a software called Iris, which classifies each pixel into one of two classes, sea ice or leads. You can visually inspect our region of interest in the image and the mask by plotting them here. Next, we will divide our single training image into a series of 3x3 pixel patches, which will be used as the individual samples in our datasets. Each patch will be labeled by the class of the center pixel, and the surrounding pixels will serve as spatial information in our models. Since we need each patch to be 3x3, we will exclude the outermost layer of pixels from the image. After performing this operation in this for loop, we are left with about 59,000 patches that are 3x3x21. The 21 here corresponds to the 21 color bands from the Sentinel-3 satellite image. Next, we divide these patches into test and training sets using a 9:1 ratio. You'll notice here that we have a lot more patches that are labeled by class 0, which is sea ice. This could pose a problem for our models because the models can become biased towards the majority class. To understand this, imagine that you had a dataset that was 99% composed of just one class and 1% of the remaining class. Your model could achieve 99% accuracy just by outputting class 1 every single time. To avoid this problem, we want to balance our datasets so that each class is represented roughly equally in the training sets. Finally, after balancing our datasets, we will export our training and test sets to be used in the next notebook. This notebook will be used to build, train, and test our models. Just like in the last notebook, we'll get started by installing, importing, and setting our local paths. After that, we'll load in the training and test sets that we created in the last notebook. The first model we build will be a convolutional neural network, which is a common machine learning algorithm used to detect features in images. CNNs slide kernels over input images to extract features by performing element-wise multiplication between the kernel weights and the pixel values. This generates feature maps, which are typically fed through an activation function to introduce nonlinearity, and then a max pooling layer to reduce the dimensionality of the feature maps. These pooled maps are then flattened and fed through several fully connected layers to a final output layer. Using a specified loss function, the network then backpropagates to improve the predictions over training. I decided to use a 2x2 kernel to slide over our 3x3 input images. Because this will create a relatively small 2x2 feature map, I've decided to exclude a typical max pooling layer to avoid further loss of information. To finish constructing my CNN, I add in 3 fully connected layers and then specify a loss function. Now we can train the model over 10 epochs and observe the training and validation, loss, and accuracy below. Now we can save our trained model and then plot training curves and confusion matrices to evaluate how our model has performed. The fact that our training and validation loss is decreasing over time indicates that the model has learned well and there are no signs of overfitting. Additionally, the fact that the majority of predictions lie along the diagonal of the confusion matrix indicates that our model is predicting fairly well. The next model we are training is a random forest. Random forests utilize an ensemble of decision trees, which are each trained independently on a random subset of the data. The final prediction is made by majority voting for classification or averaging for regression. Random forests can be a good model choice because they are less susceptible to overfitting. Overfitting occurs when your model is overly complex and tailored only to your training data. On the other hand, underfitting occurs when your model is too simple and does not fit your training data well. We want to achieve a fit somewhere in the middle, which fits the training data but can also generalize to unseen data. For our random forest, we are going to be starting out with 100 decision trees. Based on the confusion matrix of our trained random forest results, we can see that our random forest is slightly outperforming our CNN in terms of prediction accuracy. The final model we are building is a vision transformer, which is a deep learning model that applies the transformer architecture to image processing. Instead of using convolutional layers like CNNs, vision transformers split an image into patches, flatten them, and then process them as a sequence of tokens. Using self-attention mechanisms, vision transformers capture long-range dependencies and relationships between different parts of an image. Here you'll find the code to create a vision transformer from scratch. After specifying our parameters, we'll train the vision transformer over 20 epochs. Next, we'll plot the accuracy and loss curves. We can see from these curves that our vision transformer is outperforming our CNN. However, in comparison to the random forest, our confusion matrix shows that our random forest had better prediction accuracy than our vision transformer. You might have noticed that our CNN and vision transformer computed validation scores during training, but that we did not perform any validation on our random forest. So now we can hypertune our random forest using k-fold cross-validation. K-fold cross-validation involves splitting the dataset into k equal parts. The model is trained on k-1 parts, and then tested on the remaining fold, repeating this process k times, with each fold serving as the validation set once. The final performance is averaged across all runs. This validation technique allows us to fine-tune our model without having to use our final test set. Combining grid search with k-fold cross-validation, we find that the best parameters for our random forest is 150 decision trees with the best cross-validation score of 0.93. Congratulations! You have now saved and trained 3 different machine learning algorithms to classify sea ice and leads. Thanks for listening.